The Tennis Butler is an autonomous tennis ball recovery system intended for use at a tennis court. We've designed this system for the UNLV EE497 Fall 2018 Senior Design Competition. A typical tennis ball machine holds 50 to 300 tennis balls. Normally, after hitting these balls, they must either be collected by hand or with such tools as a ball hopper or a large ball mower. The only competitive tennis ball collection system that is automated is the Tenabot. Originally conceived as a 2016 Auburn University student project, this system is a ball collecting robot with mobile app. They did just complete a Kickstarter for 180 units, but their retail price is $1,000. We believe that we can provide a more robust and less expensive system. The Tennis Butler will collect, store, and transport 100 tennis balls. It is a fully autonomous system, self-driven, using cameras and other sensors such as LiDAR to locate tennis balls, plan a route, and to collect the balls in an optimal sequence. Additionally, the Tenabot will be able to return to a home position to deliver collected tennis balls, such as to a tennis coach or player practicing their serving. The mobile application will run on both iOS and Android, built on Xamarin, and will provide status information, remote control of the Tennis Butler, and control over geofencing. It will communicate over Bluetooth Low Energy for ease of use. The rover, tracker, and mobile application will communicate with one another and coordinate their activities. A tracker placed on the net post will perform computer vision analysis of the court, assessing where tennis balls are located, generating a map of the tennis court, and planning the route for the rover. Computer vision and sensors in the rover will allow it to home in on tennis balls for collection. The mobile app will allow users to set a home location where the rover will return to deliver tennis balls. The mobile app will allow you to control geofencing, to view the onboard camera and the status of the rover, as well as to manually drive the rover for demonstration purposes. The final prototype design for our EE497 class is shown here. During the design of the Tennis Butler, we discovered that most tennis balls end up at the back of the court, whether during serving practice or when returning tennis serves. Even with a high-resolution camera and a relatively narrow field of view, the tracker has trouble resolving individual tennis balls, which can be as few as 10 pixels across. We need a better solution. The introduction of LiDAR allows for the rover to detect tennis balls and other obstacles nearby. Our choice is the RP LiDAR A1M8. It is an inexpensive trigonometric LiDAR system with a typical range of 6 meters and a 1 degree resolution. It is able to scan a full 360 degrees every 5 seconds. The provided ROS node publishes received data from the LiDAR for every 360-degree sweep as an array of distances. This information can be visualized in RViz as a polar plot as shown at right, showing the LiDAR's surroundings. The addition of LiDAR will greatly improve our ball collection and collision avoidance capabilities in combination with the information from the tracker module. We've already developed a ball detection algorithm in OpenCV. Given that tennis balls have a distinctive color and a known diameter, we can locate elements of an image or video stream that contain tennis balls, finding the centroid of the mask and estimating the distance to those balls. Our computer vision workflow is fast and efficient. We generate a mask of near white colors in the image, perform edge detection and a whole line transform. We use k-means clustering to group lines at right angles to one another, and then use the ransack algorithm to estimate the intersection points of lines on the court. Given this information and the knowledge that all points lie within the same plane, we can generate a planar homography transformation that allows us to create a 2D map of the tennis court. This map, in conjunction with the rover, allows us to locate tennis balls and plan a route for the rover to collect them. Our next steps for the project are to rapidly develop a new prototype and validate our design. It will be necessary to refine this prototype based on the real-world experience we have with the system. Additionally, control system design will be critical to the success of this project, both for controlling the speed of the drivetrain and for the thrower motors. This concludes our EE497 presentation video. Thank you for listening.